In this section, we're going to be talking about parametric equations of lines. So you've dealt with lines before. If I asked you to write the equation of a line, you'd probably write y equals mx plus b, right? Or something similar. And this is great in R2. This is a line in two-dimensional space in R2. But this is not a line in higher dimensions like R3, or for any n-dimensional space where n is bigger than 2. Okay, so it's great for two-dimensional space, but it's not great for three-dimensional space. And lines are useful, lines are important. So we want a way to describe lines that works for any number of dimensions, not just two-dimensional space. So what we're going to do is we're going to use what we know about vectors to construct a new way for describing the equations of lines that works in higher dimensions. Now I'm going to draw in two-dimensional space just because it's easier to draw in two-dimensional space. But the goal here is to find an equation that works for higher dimensions, okay, using the math of vectors. So the first thing that we may note is that if we have a vector let's call this vector v. If we scale that vector, it will always be pointing in the same direction or in opposite direction, right? So I could scale it to be twice as long like that, or half as long like that, or multiply it by a scalar of -1 and I'd get that, right? In fact, if we think about all possible scalars that we can multiply this vector by, we would end up getting a line pointing parallel to the vector, right? So this is a very simple way to construct a line, not just in two dimensions, but this would work in any number of dimensions because we have vectors in any number of dimensions. So this line here is just a variable scalar, t, times a direction vector, v. This gives us a line through the origin in the direction of vector v. Okay, and I just want to emphasize v would be a known vector. We would know it beforehand. It would be the direction vector for our line. T, though, is a variable. So if you plug in different values of t, you get different values along the line. If I plug in t equals 1, I get the point right here. Okay, I move in the direction of 1v. If v is 2, I end up right about here, right? It'd be that point along the line. If v is -0.5, I go the opposite direction and I go half the distance of v, half the length of vector v. Okay? So t is a variable, but v is a concrete vector, a known vector, not a variable. If I plug in different values of t, I get different points along the line. So that's great. We have a way to describe a line, not just in two dimensions, but in any number of dimensions. But there's a limitation. This only works for lines through the origin. Okay, because if I plug in t equals 0, then I end up at the origin, right? Fortunately, it's easy to adapt this to work for lines going through other points. Okay, so for example, suppose we want to describe the equation of a line passing through the point x sub 0 and with direction v. Okay, so we have a point that the line is passing through. We also have a direction the line is in. So again, I'll draw my example in 2 dimensions, but this holds for any number of dimensions. Okay, so let's say my point x sub 0, let's say it's right here. Okay, and so vector x sub 0 is pointing to point x sub 0. We kind of identify them the same way. And then we have a direction vector, which I will draw with its tail at the point on the line. Let's make our direction vector, say, this way. So that's our direction vector. And so our line passes through the point and in the direction of vector v. Okay, so there's our line. Okay, so what we can do is once we reach this point, once we reach x naught, once we're on the line, as long as we're traveling in the direction of v, as long as we're scaling v, then we'll stay on the line, right? So the idea here is to use vector addition. And so the equation of this line, I'm first going to get to the line. So I go from the origin to the point on the line, and then once I'm on the line, I can move any scalar multiple of v. Okay, so if we kind of think about this as displacement, I'm going to first travel in the direction of x naught. So I first get to the line, and then once I'm there, I move a multiple of vector v, a scalar multiple of vector v. Okay, vector v tells me my direction, but t is a variable. It could be anything. So if it's 2, I go 1, 2 units in the direction of v. I'm on the line, right? If t is a different value, maybe it's -1. So once I get to x naught, then I move in the negative direction of vector v. I'm still on the line, okay? So this is the general formula for a line that will work in any number of dimensions. So let's summarize that. Okay. A line that passes through some point, which I'll call x naught, and travels in the direction. let me not use travels. The line doesn't really travel. Let's just say with direction. V can be represented by the vector equation so I'm going to call this x of t. It's a vector equation, so I'll end up with a vector at the end, but it depends on variable t. Different values of t will give me different points along the line. Okay, and it's my chosen point on the line plus t times the direction vector, the direction of the line.